uh, Debuggee in Java Debugger. Now we are focusing on Debuggee. The Debuggee is the process being debugged. It consists of the application being debugged, the VM running the application, and the backend of the debugger. We can here consider JVM tool interface. The JVM TM JVM tool interface JVM TI is a programming interface used by development and monitoring tools. It provides both a way to inspect the state and to control the execution of applications running in the Java virtual machine VM. Now we are focusing on VM. This refers to the VM running the application being debugged. The debugger architecture is being designed for use in wide spectrum of VM implementations. The VM implements the Java Virtual Machine Debug Interface JVM TI. Here you can see a JVM architecture diagram. A virtual machine is a software implementation of a physical machine. Java was developed with the concept of WORA, write once, run anywhere, which runs on a VM. The compiler compiles the Java file into a java.class file. Then that .class file is input into the JVM, which loads and executes the class file. Below this is a diagram of the architecture of JVM. As shown in this architecture diagram, the JVM is divided into three main subsystems: class loader subsystem, runtime data area, and execution engine. Class loader subsystem. Java's dynamic class loading functionality is handled by the class loader subsystem. It loads and links and initializes the class file when it refers to a class for the first time at runtime, not compile time. Loading. Classes will be loaded by this component: bootstrap class loader, extension class loader, application class loader are the three class loaders that will help in achieving it. Bootstrap class loader, responsible for loading classes from the bootstrap class path, nothing but rt.jar. Highest priority will be given to this loader. Extension class loader, responsible for loading classes which are inside the ext folder jre /lib. Application class loader, responsible for loading application level class path, mention, environment variable, etc. These class loaders will follow delegation hierarchy algorithm while loading the class files. Linking verify. Bytecode verifier will verify whether the generated bytecode is proper or not. If verification fails, we will get the verification error. Prepare. For all static variables, memory will be allocated and assigned with default values. Resolve. All symbolic memory references are replaced with the original references from method area. Initialization. This is the final phase of class loading. Here all static variables will be assigned with the original values and the static block will be executed. Runtime data area. Runtime data area is divided into 5 major components. Method area. All the class level data will be stored here, including static variables. There is only one method area per JVM and it is a shared resource. Heap area. All the objects and their corresponding instance variables and arrays will be stored here. There is also one heap area per JVM. Since the method and heap areas share memory for multiple threads, the data stored is not thread safe. Stack area. For every thread, a separate runtime stack will be created. For every method call, one entry will be made in the stack memory, which is called stack frame. All local variables will be created in the stack memory. The stack area is thread safe since it is not a shared resource. The stack frame is divided into 3 subentities. Local variable array. Related to the method, how many local variables are involved and the corresponding values will be stored here. Operand stack. If any intermediate operation is required to perform, operand stack act as a runtime workspace to perform the operation. Frame data. All symbols corresponding to the method is stored here. In the case of any exception, the catch block information will be maintained in the frame data. PC registers. Each thread will have a separate PC register. To hold the address of current execution instruction. Once the instruction is executed to the PC register will be updated with the next instruction. Native method stacks. Native method stack holds native method information. For every thread, a separate native method stack will be created. Execution engine. The bytecode which is assigned to the runtime data area will be executed by the execution engine. The execution engine reads the bytecode and executes it piece by piece. Interpreter. The interpreter interprets the bytecode faster but executes slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required. Just-in-time compiler. The GIT compiler neutralizes the disadvantage of the interpreter. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the GIT compiler, which compiles the entire bytecode and changes it to native code. This native code will be used directly for repeated method calls, which improve the performance of system. intermediate code generator produces intermediate code. Code optimizer responsible for optimizing the intermediate code generated above. Target code generator responsible for generating machine code for native code. Profiler, a special component responsible for finding hotspots, that is whether the method called is called multiple times or not. Garbage collector collects and remove unreferenced objects. Garbage collections can be triggered by calling system.gc method, but the execution is not guaranteed. Garbage collection of the JVM collects the objects that are created. Java native interface, JNI. JNI will be interacting with the native method libraries and provides the native libraries required for the execution engine. Native method libraries. This is a collection of the native libraries which is required for the execution engine. Here class file is connected to class loader subsystem. Linking, loading, linking and initialization is inside class loader subsystem. Bootstrap class loader, extension class loader and application class loader is inside loading. Bootstrap class loader is connected to execution class loader. Extension class loader. Extension class loader is connected to application class loader. Loading is connected to linking. Verify, prepare and resolve is inside linking. Verify is connected to prepare. Prepare is connected to resolve. Linking is connected to initialization. Class loader subsystem is class loader subsystem interact with runtime data areas. Method area, heap area, stack area, PC registers and native method stacks are inside runtime data areas. A number of threads are inside stack area. Each thread has stack frame, LVA, local variable array and operand stack and frame data inside each thread. There are PC registers for each thread here, and runtime data areas are interacting with the execution engine. Interpreter, just-in-time compiler, garbage collections are inside execution engine. Intermediate code generator, code optimizer, target code generator and profiler are inside just-in-time compiler. Intermediate code generator is connected to code optimizer. Code optimizer is connected to target code generator. Execution engine interacts with native method interface. Runtime data areas are interacting with native method interface. Native method interface interacts with native method library. As an example, we can consider this one, JDB my class. The most frequently used way is to have JDB launch a new Java virtual machine VM with the main class of the of the application to be debugged. This is done by substituting the command JDB for Java in the command line. For example, if your application's main class is my class, you use this command to debug it under JDB. When started this way, JDB invokes a second Java VM with any specified parameters, loads the specified class, and stop VM before executing that class's first instruction. JDB helps you to find and fix bugs in Java language programs. As an example 2, we can consider this. This command will run the my class application and allow JDB to connect it at a later time, and you can then attach JDB to the VM with this command. Dash attach address option attaches the debugger to the previously running VM using the default connection mechanism. Here agent lib dash agent lib colon jdwp. This option loads the JPDA reference implementation of JDWP. This library resides in the target VM and uses JVM-TI and JNI to interact with it. It uses a transport and JDWP protocol to communicate with separate debugger application. And here the transport, name of the transport to use in connecting to debugger application, here DT. This here address, the transport address at which to listen for the newly launched target VM to connect. This value is typically part of the raw command argument as well, but this is not required if the target VM has some other means of determining the transport address to which it should connect. Here the address sub option, here the server sub option. If Y listen to for a debugger application to attach, otherwise attach to the debugger application at the specified address. Suspend if Y VM start event has a suspend policy of suspend underscore all. If N VM start event has a suspend policy of suspend underscore none. As an exception example, we can consider this situation. When an exception occurs for which there isn't a catch statement anywhere in the throwing threads call stack, The VM normally prints an exception trace and exits. When running under JDB, however, control returns to JDB at the offending throw. You can then use JDB to diagnose the cause of the exception. As an error example, we can consider this: failed to connect to remote VM, connection refused. This is occurred in Eclipse IDE. Now we are focusing on backend. The backend of the debugger is responsible for communicating requests from the debugger frontend to the Debuggee VM and for communicating the response to these requests, including desired events, to the frontend. The backend communicates with the frontend over a communications channel using the Java debug wire protocol JDWP. The backend communicates with the Debuggee VM using Java Virtual Machine Debug Interface JVM TI. Here you can see a JVM TI architecture, and agent controls a JVM through JVM TI. Both share the same operating system process. The Java Virtual Machine Tool Interface JVM TI is the interface offered by the Java VM for its manipulation and control. Originally called Java Platform Debugger Architecture JPDA and used in the context of debugging, it was extended to support other use cases such as monitoring and profiling. JVM TI exposes C functions to manipulate Java VM. The JVM TI client, so-called an agent, queries and controls the given JVM, and agents share the same operating system process. JVM TI agents are meant to be written in C to be as compact as possible and allow maximal control with minimum instruction. JVM TI provides introspection and some limited intercession facilities at VM and language levels. In particular, it provides memory and heap management, thread control, execution task manipulation, object and class manipulation, and breakpoint support. JVM TI is used mainly for debugging, monitoring and analysis purposes, particularly profiling and thread analysis. Here you can see a agent is here. Agent is connected to JVM TI. Control is passed from agent to JVM TI. JVM TI is inside VM. Agent, VM and applications are inside monitored VM. Here you can see agent, application and VMs are in the operating system process. As an example, we can consider this. This is in C language. Hash include jvm ti.h. Agents can be written in any native language that supports C language calling conventions and C or C++ definitions. The function, event, data type, and constant definitions needed for using JVM TI are defined in the include file jvm.ti.h. To use these definitions, add the j2sc include directory to your include path and add hash include jvm.ti.h to your source code. Here the jvm.ti.h include file for Java virtual machine tool interface. As an example 2, we can consider this code, this one in C language. The get source debug extension for the class indicated by KLASS, return the debug extension via source underscore debug underscore extension underscore ptr. The returned string contains exactly the debug extension information present in the class file of KLASS. This one may only be called during the start or the live phase. As an optional functionality, might not be implemented for all virtual machines. Here the KLASS in J class type, the class 2, this is the class 2 query, the source underscore debug underscore extension underscore ptr in character asterisk. The agent passes a pointer to a char string. On return, the char string points to a newly allocated array. The array should be freed with deallocate. As an example 3, we can consider this one in C language, this code segment. If an agent is started during the onload phase, then its agent library must export a startup function with this prototype. This will be called early enough in the VM initialization that system properties may be set before they have been used in the startup of the VM. The full set of capabilities is still available. Note that capabilities that configure the VM may only be available at this time. No bytecodes have executed, no classes have been loaded, no objects have been created. The VM will call the agent underscore onload or agent underscore onload agent name function with options as second argument. That is, using the command line option examples, option 1, option 2 will be passed to the char asterisk options argument of agent underscore onload. The options argument is encoded as a modified UTF-8 string. If equal options is not specified, a zero length string is passed to options. The lifespan of the options string is the agent underscore unload or agent underscore unload agent lib name call. If needed beyond this time, the string or part of the string must be copied. The period between the agent underscore unload is called, and when it returns is called the unload pace. Since VM is not initialized during the unload pace, the set of allowed operations inside agent underscore unload is restricted. The agent can safely process the options and set event callbacks with set event callbacks. Once VM initialization event is received, that is, the VM init callback is invoked, the agent can complete its initialization. The return value from agent underscore unload or agent underscore unload underscore agent lib name is used to indicate an error. Any value other than 0 indicates an error and causes termination of the VM. As an example we can consider this one, the basics to find trace info in C language. Inside the agent itself, there is a trace info struct, and the pointers to these structs will serve as the value of the object tags. A tag is any 64-bit value. Along with the trace info struct is support code to create a hash table for quick lookups. Because the creation or lookup of trace info will probably consume much application time when this agent is activated, speed and efficiency are important. Here are some basics to find trace info. If thread equal null, that usually means that the VM initialization has not yet occurred, so you cannot get a stack trace. Calling get stack trace could also return an error message that the VM is not in the live phase, but a value jvmti underscore error underscore none indicates that you did not get a stack trace. Performing lookup or enter of this stack trace into the hash table will return a reference to a trace info structure. This pointer to a trace info struct will then be used as the tag on this object. all objects allocated from the same stack trace will have the same tag. When saving away stack trace information, pay attention to the trace info struct and the number of stack traces received. There should be only one stack trace of an allocation bytecode, new array bytecode, and but how many stack traces will that be? It depends on the application, but it's somewhat limited. Also, no cleanup is occurring in lookup or enter, so a very long running application could experience some problems if the total number of allocation traces is very high. The hash table is also a fixed size. Another potential problem: to avoid performance issues, being aware of the crucial sections, one of which is the lookup or enter function is crucial. Using too many crucial sections could dramatically slow the entire application. The thread used here is the current user thread, limited what you are doing in these threads. The object allocations and object free events are fairly crucial section free with regards to this particular agent. VM ti underscore event underscore VM underscore init. After the VM underscore start event and approximately several hundred class load events, the VM will reach the fully initialized event. That is about initialization. Here the thread could be null in some situations, so be careful. Here the request stack trace. If you get a pace error, the VM isn't ready or it died. If error not equal vmti underscore error underscore none, you have a serious problems. Here look up this entry here, look up or enter. If thread equal null, it's assumed that this is before VM underscore start, but technically this should not be should not happen. No tracking yet. As an exception, here we can now we are considering agent command line options in introduction in JVM-TM tool interface. So here dash agent lib name equal options. The name following dash agent lib colon is the name of the library to load. Lookup of the library, both its full name and location, proceeds the platform in a platform specific manner. Typically, the agent lib name is expanded to an operating system specific file name. The options will be passed to the agent on startup. For example, if the option dash agent lib colon foo equal opt1 opt2 is specified, the VM will attempt to load the shared library foo.dll from the system path under the Windows TM or libfoo .so from the ld-library-path under Linux. If the agent library is statically linked to the executable, then no actual loading takes place. Now we are considering agent startup onload phase. Other phase is live phase. Here, if an agent is started during the onload phase, then its agent library must export a startup function with the following prototype. Or statically link agent named L with the following function. The VM will start the agent by calling this function. It will be called early enough in VM initialization that system properties may be set before they have been used in the startup of VM. The full set of capabilities is still available. Note that capabilities that configure the VM may only be available at this time. No bytecodes have executed, no class have been loaded, no object have been created. The VM will call the agent onload or agent onload agent lib name function with options as the second arguments. That is, using the command line option examples of opt1 and opt2 will be passed to the char strict options argument for agent onload. The options argument is encoded as a modified UTF-8 string. If option is not specified, a zero length string is passed to options. The lifespan of option string is the agent onload or agent onload agent lib name call. If needed beyond this time, the string or parts of the string must be copied. The period between the agent onload is called, and when its return is called on the onload phase. Since VM is not initialized during onload phase, the set of allowed operations inside the agent onload is restricted. The agent can safely process the options and set the set event callbacks with set event callbacks. The VM initialization event is received, that is VM init. Callback is invoked. the agent can complete its initialization. Rationale, the early startup is required so that the agent can set the desired capabilities, many of which must be set before VM is initialized. In JVM-DI, the Xdebug command line option provided very coarse-grained control of capabilities. JVM-PI implementations use various tricks to provide single JVM-PI on switch. No reasonable command line option could provide the fine grain of control required to balance needed capabilities versus performance. In fact, early startup is also needed so that agent can control the execution environment, modifying the file system and system properties to install their functionality. Return value of the agent unload or agent unload agent lib name is used to indicate an error. Any value other than 0 indicates an error and causes termination of the VM. Now we are considering bytecode instrumentation. Assuming that the constructor is initially empty, the constructor could be changed to this. This interface does not include some events that one might expect in an interface with profiling support. Some examples include full speed method enter and exit events. The interface instead provides support for bytecode instrumentation, the ability to alter Java virtual machine bytecode instructions which comprise the target program. Typically, these alternations are to add events to the bytecode of a method. For example, to add at the beginning of a method call to myprofiler.method entered. Since the changes are purely additive, they do not modify the application state or behavior. Because the inserted agent code is standard bytecode, the VM can run at full speed, optimizing not only the target program but also instrumentation. If the instrumentation does not involve switching from bytecode execution, no expensive state transitions are needed. The result is high performance events. This approach also provides complete control to the agent. Instrumentation can be restricted to interesting portions of the code, for example, the end user's code, and can be conditional. Instrumentation can run entirely in Java programming language code or can call into native agent. Instrumentation can simply maintain counters or statistically simple sample events. Instrumentation can be inserted in one of three ways. Static instrumentation: the class file is instrumented before it is loaded into the VM. For example, by creating a duplicate directory of *class files which have been modified to add instrumentation. This method is extremely awkward, and in general, the agent cannot know the origin of the class files which will be loaded. The next way, load time instrumentation: when the class file is loaded by the VM, the raw bytes of the class files are sent to the instrumentation to the agent. The class file load hook event triggered by the class load provides this functionality. This mechanism provides efficient and complete access to one-time instrumentation. Other one is dynamic instrumentation. A class which is already loaded and possibly even running is modified. This optional feature is provided by the class load hook event triggered by calling retransform class function. Classes can be modified multiple times and can be returned to original state. Mechanism: the mechanism allows instrumentation which changes during course of execution. The class modification functionality provided in this interface is intended to provide mechanism for instrumentation. The class file load hook event and the retransform classes function, and during the development for fix and continue debugging, the redefine classes function. Care must be taken to avoid perturbing dependencies, especially when instrumenting core classes. For example, an approach to getting notification of every object allocation is to instrument the constructor on object. Assuming that the constructor is initially empty, the constructor could be changed to this. However, if this change was made during class file load hook event, then this might impact a typical VM as follows. A first created object will call the constructor, causing a class load of myProfiler, which will then cause object creation. And since myProfiler isn't loaded yet, infinite recursion, the resulting in a stack overflow. A refinement of this would be to delay invoking tracking method until the save time. For example, track allocations could be set in the handler for the VM init event. The set native method prefix allows native methods to be instrumented by use of wrapper methods. Now we are considering accessing functions in functions. When used from the C language, the double indirection is used to access the functions. The environment pointer provides context and is the first parameter of which function call. For example, JVMTI error get loaded classes, JVMTI env pointer env, and jinit strict class count pointer. Sorry, jinit asterisk class count ptr, jinit class ptr, return, and here the return an array of classes loaded in the virtual machine. Number of classes in the array is returned via class count pointer, and the array itself via classes pointer. The native code accesses JVMTI features by calling JVMTI functions. Access to JVMTI functions is by use of an interface pointer in the same manner as Java native interface JNI functions are accessed. JVMTI interface pointer is called environment pointer. An environment pointer is a pointer to an environment and has the type JVMTI env asterisk here. An environment has information about its JVMTI connection. The first value in the environment is a pointer to the function table. The function table is an array of pointers to JVMTI functions. Every function pointer is at a predefined offset inside the array. When used from the C language, double indirection is used to access the functions. The environment pointer provides a context and is the first parameter of a function call, for example, here. When used from C++ language, functions are accessed as member functions of JVM TI env. The environment pointer is not passed to the function call, for example here. Unless otherwise stated, all examples and declaration in this specification use the C language. A JVM TI environment can be obtained through JNI invocation API get env function. Each call to get env creates a new JVM TI connection and thus new JVM TI environment. The version argument of get env must be JVM TI version. The return environment may have different version than the requested version, but the return environment must be compatible. The get env will return JNI underscore e version if a compatible version is not available. If the compatible version is not available, then JVM TI is not supported, or JVM TI is not supported in the current VM configuration. Get env will return JNI underscore e version. Other interfaces may be added for creating JVM TI environments in a specific context. Each environment has its own state. For example, desired event handling functions, desired events, event handling functions, and capabilities. An environment is released when with dispose environment. Thus, unlike JNI, which has one environment per thread, JVM TI environments work across threads that are created dynamically. Now we are considering single step in event index in events. The void init call single step JVM TI env pointer JVM TI environment JNI environment pointer JNI underscore event environment JThread thread JMethod ID method JLocation. The single step events allow the agent to trace thread execution at the finest granularity allows by the VM. A single step event is generated whenever a thread reaches a new location. Typically, a single step event represents the completion of one VM instruction as defined in the Java virtual machine specification. However, some implementation may define location differently. In any case, the method and location parameters uniquely identify the current location and allows the mapping to source file and line number when that information is available. Now we are considering data types. Here JBoolean holds a Java programming language Boolean unsigned 8-bit. Now we are considering constant index. Here the JVMTI class status array. The value is 16. The bits value is 16, and the class status flag. Class is an array here. Class is an array. The JVMTI class status array. The value is 16. Here the class here the class is an array. If set, all other bits are 0. An example, we can consider this one. This exception in C language. This is a asynchronous exception object of type J object in stop thread. As an error example, we can consider JVMTI error. This is in C or C++. This is type JVMTI error. This holds an error return code. You can see the type declaration here, type def. As an error example 2, we can consider this one, error server being server debug worklight. Error cannot load this JVMTI agent twice. Check your Java command line for duplicate JDWP options. Error occurred during initialization of VM. This is occurred in the environment of with Eclipse plugin IBM Worklight Developer Edition.